Hello everyone. For today we're going to be taking a look at section 8.4, which is about calculating the area of triangles. This might be something that you're already familiar with, but either way we're going to take a look at it and take a look at a couple things that might be tricky about it, but otherwise it's not really all that bad. First of all, we need to define what the height of a triangle represents. How do we measure how tall, if you will, a triangle is? Well, by definition, the height of a triangle is the perpendicular segment. So it's the perpendicular segment that extends from a vertex to the line containing the opposite side. And in a minute you'll see why it doesn't just say perpendicular segment extending from a vertex to the opposite side. We'll figure out why it says from a vertex to the line containing the opposite side. That'll be clear in just a second. First of all, another thing you need to know is when we're talking about this height going from a vertex to the opposite side, that makes the opposite side now the base of the triangle. And these two words, height and base, are both involved in the formula for area of a triangle. So if I look down here, I'm going to look at three different types of triangles: a right triangle, an acute triangle, and an obtuse triangle. And I'm going to look at how the height ends up showing up kind of differently in each one of these. So to start with, we have this right triangle right here. Now you'll notice at this vertex, we have a line segment that goes from this vertex down to the opposite side and makes a right angle. In other words, this side of the triangle is going to be our height of this triangle because it does exactly what the height is supposed to do. It extends from a vertex to the line that contains the opposite side, and it's perpendicular to that opposite side. So that is going to be the height, and just by way of kind of clarity, that would make then this side right here, that would make this side the base, which I'm just going to use a lowercase b for. So this side is the base. This measurement right here would be your height. So in a right triangle, the height is actually one of the sides of the triangle, and the base is also one of the sides of the triangle. Now over here we have an acute triangle, and we're going to measure the height of this triangle. We're going to try and define the height of this triangle from this vertex right up here to this opposite side down here. Now, according to the definition, what we need to do is we need to draw in a perpendicular segment that goes from this vertex down to this side. So that's going to look something like this. It's going to come down from this vertex to this opposite side. It's going to be perpendicular to it, so there'll be a right angle there. And now this measurement right here, from that down to the base down here, that's our height. And like I just said, this side measurement right here, that would be our base. So our height from this top vertex down to this bottom side, and then that bottom side would be the base. Now things do get a little bit more tricky when you're looking at an obtuse triangle and how we might measure the height of this obtuse triangle right here. And as it says, it's the perpendicular segment that extends from a vertex to the line containing the opposite side. So if I go to this vertex right here, I can't just go to this opposite side with a segment that's perpendicular to it. Any segment that I draw from this vertex down to this side, it's not going to be a right angle. It's going to be impossible to draw a segment that's perpendicular to this right here from this vertex. And that's where that part about the line containing the opposite side comes in, because what I actually have to do here is I have to take this side and I have to extend it out this way. So I'm going to kind of extend that side out this way. And then if I go from this vertex and I drop a segment that comes down from this, that's perpendicular to this extended side. So in other words, if I drop a segment down that looks something like that, got a little crooked there at the end, but you get the idea. That's going to be perpendicular right there. This measurement now is the height of this triangle from this vertex down to where the base is. The base of this triangle now would not be this entire distance from here over to here. That's not the base. The base is still this opposite side right here. So this measurement right here is the base, even though the line segment we're using as the height comes down way over here. Here's our base, and then this measurement would be our height. So with that squared away, with this idea of the height of a triangle hopefully being a little bit more clear to you now. Um, we can take a look at the formula for the area of a triangle. The area of a triangle is going to be 1/2 the base times the height. Or the way you'll usually see this written is A equals 1/2 BH, where B is base and H is height, obviously. You could, if you wanted to, write it as base times height divided by 2, because multiplying by 1/2 is the same as dividing by 2. Either way you like it, that's the formula for the area of a triangle. 1/2 base times height, or base times height divided by 2. So if I look at these three examples right here, the question is asking which of the following triangles appear to have the largest area. So we have a right triangle here, we have an acute triangle, and we have an obtuse triangle. Let's go through and real quickly calculate the area of each one of these triangles. Over here with our right triangle, like we just mentioned, this side of the right triangle can be the height, and this side right here can be the base. So if we're using A equals 1/2 base times height for this triangle, we're looking at 1/2 of 8 times 12, which would be 1/2 of 8 times 12 is 96, and half of 96 would be 48. So this triangle's area is 48. This acute triangle also has a height of 12 and a base of 8. So you might be able to guess, well, this should be the same area, right? We can verify it, and I'll tell you what I'm going to do is I'm just going to go ahead and use this other version of the formula just to see how that would look. A equals base times height divided by 2. So that would be area equals 8 times 12 divided by 2, which again is 96 that we're dividing by 2, and that again comes out as 48. Here we have our obtuse triangle, and like we just talked about, the height of the obtuse triangle ends up being this measurement that's kind of outside the triangle. So that will be our height. This time it's 8, and our base is 12. So you'll notice the measurements kind of got flip-flopped. For these two triangles, height was 12 and base was 8. Now we got height of 8 and base of 12, but it shouldn't change the area, right? Our area will be 1/2 base times height, which is 1/2 of 12 times 8 in this case, but 12 times 8, same as 8 times 12, it's still 96. Half of 96 is going to give us 48 for our height. So you can see these three triangles, even though they are obviously very different in terms of their shape, they do all come out to have the same area. And we also saw how we can kind of use that other version of the area formula there if we want to. In our next example, we're going to look at the area of a couple similar triangles. So for part A, it says find the ratios of the areas of these two similar triangles. These triangles would be similar by side angle, side similarity. Let's find the area of this larger triangle first. Of course, this 5 can be our height, and the 7.5 can be our base, because the segment that's 5 is perpendicular to the segment that is 7.5 units long. So that can be our height, that can be our base. Area is going to equal 1/2 base times height, or in this case that will be 1/2 of 7.5 times 5, and half of 7.5 times 5, well, that would be half of 37.5, and half of 37.5 is going to be 18.75. So the area of the larger triangle is 18.75. I'll go ahead and write it maybe inside the triangle. Let's do the area of the smaller triangle. We're looking at 1/2 base times height. So this is going to be 1/2 of, in this case, the base would be the 4.5 and the height would be the 3. So 1/2 of 4.5 times 3. And 4.5 times 3 is going to be 13.5. And half of 13.5 is 6.75. So that area is 6.75. Now it says find the ratios of their areas. So that means we need to take that 18.75 and put it over 6.75 and reduce that. Now it does have these decimals in it. So the first thing we're going to do is we're going to multiply both of these times 100, because what that does is it gets rid of my decimal. It turns into 1,875 over 675. And to reduce this, I can either type 1875 divided by 675 in my calculator and then ask my calculator to convert that to a fraction, which is probably the way I would do it. Or you might notice that there's actually a common divisor here of 75. And either way, if I could divide both of these by 75 or I ask my calculator to reduce this, I'm going to get 25 over 9. So 25 over 9 is my ratio for these areas. Part B asks me to find the scale factor of the larger triangle to the smaller triangle. Now remember, to find scale factor, all we do is we pick out a side of one triangle and put it over the top of the corresponding side of the other triangle. So what I could do here is I could put that side that's length 5 over here for the big triangle and put it over the side that has a length of 3. Now I would reduce this if I could, but 5 over 3 you can't reduce. So that's our scale factor right there. That is the scale factor for the large triangle compared to the small triangle. The second part of this says, how does it compare to the answer of part A? Well, the answer of part A was 25 over 9. So how does 5 over 3 compare to 25 over 9? And you might realize that if I take the 5 and I square it, I get 25. And if I take the 3 and I square it, I get 9. So the scale factor was 5 over 3, and the areas had a ratio of 25 over 9. And that leads us to a conclusion we can draw for theorem 8.3. It says that if two polygons are similar, like we had similar triangles up here, and they have a scale factor of A over B, then the ratio of their areas will be, well, we just figured that out, right? Scale factor was 5 over 3. Ratio of the areas was 5 squared over 3 squared, or 25 over 9. So what we can put down here is we can put A squared over B squared. So if the scale factor is A over B, the ratio of the areas will be A squared over B squared. Now the last thing we're going to be taking a look at is this example of finding the area of a triangle where we actually are missing one of the measurements that we need. And we need to find the area of this triangle. It's a right triangle. One side of it is 5. And actually, for simplicity's sake, I'm going to change that to a 13. So we're going to have a side of 5 and this side that's 13. Now, this isn't base and height. One of the things that you need to remember, you can probably write this down in your notes, give yourself a little reminder. The height is always going to be perpendicular to the base. Height will always be perpendicular to the base. And as you can see here, the side that's 5 units long and the side that's 13 units long, those are not perpendicular. They don't meet and form a right angle. The side that's 5 is perpendicular to this unknown side up here. So what we're going to use is we're going to use this Pythagorean theorem to find this missing measurement right there. So remember, the Pythagorean theorem is a squared plus b squared equals c squared, where c is always the hypotenuse, which means that in this problem, my 13 is going to be my c. So that's going to go right there. The other two sides will be a and b, and I guess since this one's already called b, we'll let it stand in where the b squared is, and then this will be our a. So we have an equation that says 5 squared plus b squared equals 13 squared. Now what I'm going to do is I'm going to rearrange this and say that b squared then would be 13 squared minus 5 squared. And if I type in 13 squared minus 5 squared on my scientific calculator, it will tell me that b squared needs to be 144. Well, that would mean then that if I square root both sides, b would equal the square root of 144, which is 12. So this side right here now is 12. My area formula again is 1/2 base times height. So in this case, I'm going to use the 12 as my base. So 1/2 of 12 times, and the height will be 5. 1/2 of 12 times 5, that is 1/2 of 60. And 1/2 of 60 will be 30. So the area of this triangle right here would be 30 square units if we wanted to give it a label. So there you have it. Formula for area of a triangle is 1/2 base times height. And always remember that the height will be perpendicular to the base in every instance, in every formula that we're going to learn. When it talks about height and base, those two things should always be perpendicular to each other. Okay, we'll see you for the next lesson.